In section 11.3, we're going to look at what we call contingency tables, or two-way frequency tables. And what these are tables that compare two variables to each other and we're going to test those tables for independence. So this can best be seen looking at an example. So in this example, we have a table below summarizing the challenges made by tennis players in the first US Open that used the Hawkeye electronic instant replay system. We're going to use a 0.05 significance level to test the claim that success in challenges is independent of the gender of the player. Then we'll answer, does either gender appear to be more successful? So this is what we call a contingency table, or a two-way frequency table, in which frequencies correspond to two variables. So the two variables in this case are the gender and the success of the challenge. So the frequencies we get is 201 out of all of them was successful for men. 288 challenges were not successful out of all of them, but for men. So we're comparing the gender to the success in challenges, and we're asking the question, are they independent? So we test these two variables for independence. The null hypothesis is always going to be, in these cases, that the row and the column variables are independent. So step one, again, we'll identify the claim. In this case, the success in challenges is independent of gender. Step two is the opposite. How successful a person is in challenges depends on their gender. So in other words, it's not independent, it does depend on the gender, is what the opposite is saying. The null hypothesis will always take on the independence, and the alternative hypothesis will be dependence. We're going to use a significance level of 0.05, and we'll use the same test statistic that we used in 11.2. The question now, though, becomes, how do we find the expected frequencies of each cell? So how do we find the expected frequencies for men's successful challenges, for men's unsuccessful challenges, the expected frequency for women's successful challenges, and women's unsuccessful challenges? To do this, we're going to create another table that's going to hold those expected values. So let me walk through these step by step. The first thing we want to do is add up the columns and add up the rows. That'll make our further calculations a little bit easier, so we don't have to add up the rows and columns every time we need them. So the expected frequency for a specific cell is going to be the row total that that cell is in times the column total that that cell is in, divided by the grand total of everything. So to get the grand total, we can either add up the two column totals or the two row totals. They should come out to be the same number. In this case, it looks like it'll be 839 will be the grand total. So let's first look at the top left column. So in this case, I want to know the expected frequency for the men's successful challenges. So the row total, we'll be looking at the row that 201 is in. So of course it's in the top row. So the total for that row is 489. The column total for the column that 201 is in will be 327. And the grand total, of course, we said, is 839. So throwing this into the calculator, I get 190.59, and that will go into the top left cell of my expected frequency table. Next thing we'll do is do the same thing, but this time for the upper right cell, where 288 is. So the row total for that row is still 489, but what changed with 288 is the column that it's in. So the column total for 288 is 512. I'll divide everything by 839, again, the grand total, and we get 298.41. So let's do the same thing for the lower left cell. the row total for 126 row will be 350. And the column total will be 327. And the grand total stays the same at 839, which gets us 136.41. Lastly, for the lower right, the row total is 350, and the column total is 512, and the grand total is 839, which gets us 213.59. Now, all we've done is calculate the E for each cell, or the expected value for each cell. We still need to calculate the test statistics, so that's what we'll do next. What we'll do though is take these tables and I'm going to place them into a column similar, or into a table similar to what we were working with in section 11. So our observed frequencies are going to be from our first table, or our observed table. And now it doesn't matter what order you put these numbers in, as long as the same corresponding cells appear to the right of them from our expected table. So for example, since 201 was my upper left cell, then next to 201 I should have the upper left cell from my expected table. Same thing for 288, I should have 298.41 next to it. So the key here is it doesn't matter the order that these observed frequencies go, as long as the corresponding expected frequencies are right next to them. And now we can do our O minus E column. So for our O minus E column, I'll get 10.41 for the first row, negative 10.41 for the second row, negative 10.41 for the third row, and 10.41 for the fourth row. The fact that these are all the same but possibly opposite is not a coincidence. So now we square each of those and we should get the same value in each row. But now when we divide by each of these by E, of course E is different, so the O minus E squared divided by E column should come up with different numbers. So here I took 108.3681 divided by 190.59 to get 0.5686. Do that for each of the 4 rows, and then finally add them all up to get our test statistic. In this case, 2.234. So we found our test statistic to be 2.23. Next step is to calculate the critical value. So when we have a situation like this, where we're testing 2 variables, we're going to use the degrees of freedom, the number of rows we have minus 1, times the number of columns that we have minus 1. So in this case, that leaves us a 1 times 1, or degrees of freedom 1. So looking at our chi-square distribution table, we're in the degrees of freedom 1 row. We're going to use a 0.05 significance level, which means we have a critical value of 3.841. So we found our critical value to be 3.841, but since our test statistic, 2.234, was not greater than the critical value, we're going to fail to reject the null hypothesis. So we cannot reject the null hypothesis that the challenges are independent of gender, which was the same as our claim. So in other words, we have enough evidence to support the claim that successful challenges are independent of gender.